So hi, everyone. Thank you very much for coming to the talk. And thank you very much for this event. It's really wonderful to see all of these talks. So as I said, today I'm going to be talking about a specific scheme that is called private information retrieval. So perhaps, yes, it works. Okay. So perhaps the first thing that you might ask yourself is specifically what is private information retrieval? And you will see it in the literature also called PIR, or sometimes people also pronounce it PIR. It's essentially the same. And what it is basically in a setting in which you have a database that you represent as an array of M elements. And you, of course, as a client, are interested in specifically retrieving a specific value that you know that exists in that database. So this is, again, in the setting of information retrieval. That's why it's called, that's why it has the information retrieval part in the name of the scheme. But what is the problem is that you want to add privacy to specifically these specific queries that you're sending to the server. Why you want this is because you don't want the server to actually know the specific queries and the specific values that you're interested in this database. Why would you want to actually do this is because obviously databases sometimes hold a lot of sensitive information or in general host values that you don't want the server to know because they don't want, for example, to know which specific password you're interested in checking against in a compromised checking database, for example. So what is the setting here is basically that you have a client and an amount of clients that are sending C queries against this server or a collection of servers, we will see next when this happens, that actually hold the database. And it is assuming this in this specific problem that this database is public. There's another version of this problem in which the database is private, but we will talk about that a little bit later. So what's basically the setting is, as you see here, that you as a client have an index that is assumed that you know ahead of time because the database is public, and you want to send this in the form of a query to the collection of servers or to a single server. You want the server then reply to you with an answer, and then locally as a client, you're going to be passing the specific answer and get back your value with high probability. Yep, so just like that. Okay, so if you read in the literature, you will find that basically when we talk about private information retrieval, we kind of have sort of defined a categorization of these specific schemes. And you will find out that they are a thing called information theoretical PIR, which we are not going to be talking in this talk, but I'm happy to answer questions afterwards if you're interested. And basically what they have this is in a setting in which you don't have a single server, but rather you have a collection of servers, and each one of those servers hold a copy of the database, and you're basically basing your security assumption on the assumption that this set of servers are non-colluding and they are not trying to guess with each other, basically the query or the specific index that you're interested in the database. The ones that we're going to be focusing here that are kind of more interesting from a practical application standpoint of view is the one that is called computational theoretical PIR. And what does it specifically mean? It is in the setting in which you have a single server, and then you're basing your security on the cryptographic assumptions. But here we also have already two subtypes. Why we have two subtypes is because later we're going to be seeing some of the efficiency properties of the PIR schemes. And basically what we have is that we have an efficiency in which what we want is that whatever gets downloaded from, or whatever costs your PIR scheme incurs on, is going to be less than the total cost of actually downloading locally as a client your database. Why you want this is because obviously if you could download the database locally as a client and then perform queries against this specifically locally download database, you will have kind of perfect privacy because then you can like fetch locally any kind of item that from the database that you just download. So what you want instead is that you want a PIR scheme that is much more efficient than that cost of locally downloading the database as a client. And why you will want this is because in some occasions, you as a client will not be able to download this database because it turns out that this database is too big, or because you have constrained local storage, or because you don't want to. So in those cases, you just want a PIR scheme. But it turns out that there's, as I told you, a subtype of this problem of the computational theoretical PIR, one that is called a stateless PIR. And it turns out that sometimes these specific type of schemes actually perform worse than downloading the whole database, or they require a lot of computational overheads. So in the light of these, a lot of researchers came up with a solution which is called a stateful PIR. What is a stateful PIR? It's basically the notion that you're going to be having a state that sometimes in the literature is also called a hint or a digest. What is this state? It's like a pre-computed parameters that are not dependent on the query, and then you can pre-process ahead of time because they are not dependent on the query. So what it turns give you is that it really gives you good computational and communicational times cost because you have like put a lot of the pre-computation in this pre-processing stage. And basically, what is this idea of computational theoretical PIR, specifically in the stateful mode, is that you are now going to use, obviously, cryptographic assumptions. You're going to encrypt the query instead of, for example, using information and theoretical methods, as, for example, using secret sharing. Okay, so you might think, okay, that sounds great. Now we have something that seems to be efficient because it's less than the total cost of actually downloading the database. But if you read the literature in the past, prior to some of the works that we published, you will still find that there are some limitations to computational theoretical PIR. Specifically, which kind of limitations? What we have is that it turns out that this pre-processing stage in which you just compute this specific state that is independent of the client queries, it turns out that that specific pre-processing stage, it is still too computationally heavy or sometimes too communicationally heavy. And why is this not a great thing? Is because if you are a client and you have constrained local storage, you will still have to be spending a lot of cost in this specific pre-processing stage. It also turns out that some of the schemes that have been presented in this mode, in this computational theoretical mode, have some security parameters that we don't consider, and this is an opinionated opinion, that we don't consider as practical, because, for example, some of them only arrive to 111 bits of security, when sometimes for some standardization purposes, you will want a little bit of a higher security, right? You will want 128 bits of security, for example, and it turns out that if you try to increase the security of these specific parameters, that you will not be able to actually do so, because it will heavily impact your cost again. And finally, it turns out that some of these schemes don't really have simple, open source, verified, or even available implementations, which again, if you want to put any kind of a scheme in the real world, you will have to actually have an implementation, because it makes it much more easier for engineering teams to just take this implementation and actually push it to the real world. So what is the current outlook? Is that this is a very active area of research. We have at least one paper that is published every day on ePrint. So if you're interested in this area, it is very active, and you will find papers like every day, I promise you. There's now some promising efficiency. So what I will show you in this specific talk is some of the schemes that we come up with that have good costs, so we can use them in the real world. And you have a variety of applications. Think of, for example, compromised credential checking systems or transparency logs or any kind of certificate check. You can basically try to use PIR over there. Which applications specifically that exist now that maybe are actually soon to be deployed or already deployed? We have the majority of them being used for compromised credential checking systems. What this specifically means is that you have, for example, a password or any kind of like secret kind of identifier that you want to actually check against a leaked passwords database. And you put this in the browser, so anytime that you log in, and it turns out that your password was leaked into whatever service, and then it has been put in a public database of leaked passwords, you can check if indeed it belongs to that database or not. You can also, we also found out that Google also uses PIR for device enrollment. I'm not really sure how that scheme works, but I put it here, the URL, in case you're interested. And there's also some more excitement and advances on PIR. So you can also use PIR, for example, for search engines or for recommendation systems or for even document ranking, in which what happens is that you are now also not revealing that specific query to the server. And I have put here all the links if you're interested in actually learning about them. Okay, so that is the current setting and the current outlook. And as I told you already in some 2 slides ago, we have now some schemes that indeed arrive to some good efficiency. And what are these schemes? One of these schemes is the one that is called Frodo PIR, but it's also known in the literature kind of simple PIR, because the same idea concurrently was also discovered with some researchers at the same time. So I have put here the 2 papers in case you're interested in reading. They arrive into the same scheme, but some of them have some slightly differences. So I will invite you to read both papers. And it's called Frodo PIR, as you see. And here I'm going to be already answering the question that some people posed me, which is why it's called Frodo PIR. If you're ever part of the post-quantum NIST competition, you will know that there was such a scheme that was called FrodoChem. Why was it called FrodoChem? It was because it is based on LWE, on simple learning with errors only, so they toss the ring. So because they are tossing the ring, they kind of like call it the Frodo scheme. And we follow the same approach because we are only based on simple regular LWE. So you can think of, if we extend this analogy, that is Frodo holding this ring, which is kind of the index, from Sauron, which is the one that holds kind of the database. And you don't want like Sauron to know which specific index or which specific index you're interested of that database. And that's how much I will extend that analogy, but that's basically just to answer the question that usually people pose me, or why it's called Frodo PAR. Okay, so as I told you, the idea of this scheme is that it is based only on regular LWE, and the security, because we are following out learning with errors, is basically relies on decisional LWE. We have a very conservative security. We arrived to 128 bits of security, mainly because we were interested in maybe pushing this for a standardization, and we already know that sometimes standardization bodies ask for this specific security. We can debate if this is a good number, but in any case, it's the one that sometimes seems to be chosen. And this security holds for 2 to the 52 client queries. Some parameters can actually be easily modified because the scheme is highly configurable, but we chose specifically this specific level of security. As I told you, this is a concurrent scheme that is called simple PAR, and I'm going to later show you the scheme and also highlight the differences with this specific other scheme that is called simple PAR. And we also tailored this specific scheme for real-world applications and for efficiency. So once I actually introduce you to the scheme, sometimes I'm going to highlight which specific choices we make so that it is easier actually to work with this specific scheme in the real world. Okay, so how does it look like? I'm going to be referring back to this specific slide, so don't worry if you don't get it at the first time. But it's essentially like this. So if you're really familiar with lattices, you know that this is very similar to regrets encryption. If you want the latex, you can have the latex, or you can also have it a nicer visualization of the scheme. Okay, but prior to actually introducing the scheme, maybe let's introduce first some notation. So as I told you at the beginning, PAR works in the setting in which we have a public database that is usually arranged as an array of M elements. And it is assumed that each one of those elements that belong to this specific array has at most W bits, or each one of them have W bits. And each entry in this specific array, it is indexed by an index that we're going to be calling I that corresponds to the specific position of that specific element in the array. There are obviously C clients that are going to be sending C queries against this specific database. We also, as I told you, we're going to be using LWE, so we have to set the dimension and the modulus respectively, which are going to be called N and P. And Q, rho, which is the number of bits that are packed into each entry of the database matrix. I'm going to explain that later, so don't worry. Phi, which is the uniform termini distribution, and lambda, which is the concrete security parameter. And we also have a pseudo-random generator that is going to be expanding on a specific seed that we're going to be calling mu. Okay, so let us start with the scheme by maybe going back this slide. Okay, so what I told you already about PAR is that we're going to be setting ourselves into the setting of computational theoretical PAR, which we already checked, right? Because we're basing ourselves with learning with error. And what I already told you is that there's such a subtype of this one, which is called a stateful PAR, which is basically one in you have an state, a hint or a digest that is preprocessed so that later when you send your queries, your costs are much more small. So if you already think about this, the step 1 and 2 that are happening in this slide are basically that. Those are the preprocessing stages. Why we can make this is because, as you see in the steps 1 and 2, none of those parameters, none of those values that you're computing is actually related to the query that eventually is going to be sending as a client to the server. So that's why essentially we can preprocess them. Okay, so what do? We have the server, right, who is now going to be executing the preprocessing stage. What happens at the beginning first is that the server is going to be having a setup, which is essentially a step in which the server constructs this database containing the M elements, as we already learned. And then we're also going to be sampling a seed, which, as I told you, is going to be called mu. Then it happens the actual preprocessing. What does the server do? The server derives a matrix A from that specific seed that we just had. Then they also encode the database in a matrix-like representation. I will go back to this step a little bit later. And then what they do is that they do a multiplication of A times C, and the return of this value is going to be called M. And then as a server, what they do is that they publish the pair mu and M to a public repository, a public place. So interesting to think about it. What is the hint here? The hint is this specific M. And as you see here in this step that the server just executed, there's no relationship or no actual link to the query that eventually the client is going to be sending. But as you see here, this computation is very heavy because you're doing all of this multiplication. So you're doing them ahead of time. As I told you, we're basically also encoding the database in a specific matrix-like form. Why we're doing this is because we want to later perform the specific computation, and there's many ways to actually how to represent this database. If you read a simple PIR paper, for example, you will realize that they encode in a matrix, which is the square of m times the square of m, which is basically the square encoding. But in our case, we chose to do it as n times omega, being omega equal to w over the log of rho. So what we wanted to do is essentially to have a representation of the database, which is kind of like narrow, times like this derivation of the matrix that is A, that is kind of like short. So at the end, we end up with something that is kind of like short and narrow. Why we decided to go to this encoding is because we're more interested as a client on actually being cheap. So we're not actually highlighting or taking care of the server. We're more interested in making something cheap for the client. And what is cheaper for the client is if you are ever work with AWS, you will know that the cost of upload are not so much. But if you actually check the download cost, you will see that those are heavy. So what we wanted to do is that the client doesn't have to spend so much money downloading all of these preprocessed parameters, but rather we wanted to constrain that as much as possible so it's easier for the client to download. Okay, so the server just essentially derived these and make them public, and this is called M, and it makes public mu and M. The client in turn can also have a preprocessing stage that is also optional. If you read the simple PIR paper, you will realize that this step is not in that paper because this is optional. But again, this step is not going to be dependent on the specific query that later the client is going to be sending. What does the client do? They basically download from this public repository the mu and the m. Then they also can derive this specific matrix because they have the seed, right? So they can derive A again. Then they sample C vectors, they sample C, S's, and C, E, which again, if you're familiar with regex encryption, this is already looking quite similar to that, basically the secret and the error, right? And then they also compute C, B's, and C, C's. What are the B's and what are the C's? Is basically the B's are the multiplication of S times A plus the error, and C is the multiplication of S times M. So again, if we go back some slides, this is looking really familiar again with regex encryption. As you see here, the only step that we're missing here of regex encryption is later to add the message that you're interested in encrypting in. And we're doing this because we're interested in actually saving sometimes. So later when you actually send your query to the server, it's much more cheaper to Okay, so we have that, and that is great. Now you have preprocessed your parameters, and those parameters are going to stay the same for example, X amount of queries that the client is eventually going to send. How many queries? In our scheme, we set up the 2 to the 52, but you can also increase this a little bit. It will be a little bit more costly for you, but you can increase it if you want. Now we're going to the online step. So what is the online step? Basically, as a client, I told you that you're interested in sending a query, right? What is this specific query? It's just going to be a long vector that has zeros in all of the position, except on the specific value that you're interested into the database. You create this specific vector, and you add that specific vector from one of the preprocessed parameters that you as a client locally derive. So you add B and this specific long vector of zeros, except for the position that you're interested in. And the result of this operation is called B prime. And as you see here, mostly this is cheap for the client because it's just this specific addition. If we go back, then we're saving ourselves some specific computation because we already preprocessed all of the computation of the B in this kind of preprocessing stage. And then as a client, you just only need to do the addition, which is great because it turns out then the client doesn't have to spend a lot of computational resources performing this specific operation. Once they have derived this, which is called B prime, they send B prime to the server. The server in turn receives this specific query, and then in turn does the multiplication with the encoding representation of the database that is called D, and calls the result of this specific multiplication C prime. Now here you can tell me, okay, but that looks like already like an expensive computation because it's a multiplication, and I will argue that yes, that is true. But we are more interested in saving costs for the client because we assume that the servers sometimes have more computational power. So this in turn means that the server has a little bit of more computational load, but we assume that for practical use cases, that is not so bad. Okay, and the server basically does this operation and then returns that specific value that is called C prime and send that to the client. The client receives this specific C prime and then does the subtraction with one of the local values, the C, and we have probability they're going to get back the value that they are interested in. So as you see here, what we have basically do is that we have regex encryption, and we have a kind of fragmented regex encryption such that a lot of the steps that are not dependent on the query are kind of in this preprocessing stage. And the rest that is dependent on the query is in the online phase, but they are much more cheap because you have done a lot of the bulk of the computation ahead of time. Okay, so one of the things that I said in some of the previous slides is that you want this scheme to be efficient because obviously you want to put this in the real world. So what is the efficiency here? Is basically what I told you is that PIR schemes require a communication overhead smaller than the solution of having clients downloading the entire server database. And for specifically stateful PIR schemes, we also want this to hold even when amortizing costs over the number of client queries. So what we want is basically that the cost of the communicational cost of the offline phase plus times the communicational cost of the online phase have to be less than the cost of actually downloading locally the database. So how does it look in for other PIR? Essentially, as a client download, you have the parameters, the complexities that you see here for the offline and online phases. And what we argue actually is that that is less than the size of locally downloading the database. And this usually in Frodo PIR really holds for a large C for the number of queries that the client is going to be sending. For a C that is bigger than 18,000 for an M, which is the size of the database of 2 to the 16. So as you see here, we're kind of very efficient because we will have a very big database of 2 to the 16 elements, and then the client is going to be able to execute a lot of queries during that time and still maintain efficiency. If you're interested now, not only in the complexity, but actually times, you will see here that at least on the online phase, we're very, very cheap. We're of the milliseconds, right? So for the client, this is really easy to execute because they only have to spend some milliseconds actually performing the operations. For the server, it is a little bit more costly, and that is represented in the server response as you see here, as I told you, because they're going to be performing a computation that is a little bit more heavy. One of the things that is interesting on this table for you to look at is that with kind of the parameters, kind of the times arrive to similar times, even when we increase the size of the database, because the first row here, it is the size of the database. So we have 2 to the 16, 2 to the 17, 2 to the 18, 19, and 20, and you will see that we have arrived to really nice times. We do have a lot of time spent in the offline phase of the seconds, as you see here in the rows that are like indexed by the offline value. Basically, you have a little bit more heavy times over here. You have it of the seconds because, as I told you, this is the pre-processing stage. But take this into account that this is going to hold specifically the same for 2 to the 52 queries, for example. So we do have an efficient scheme. If you're interested in actually running these specific parameters and checking against them, we do have an implementation in Rust that is available, and you can easily check if you want to double check this. Hello. Oh, okay. Yeah, that was weird. Okay. Okay, so it is working, right? Okay. Yeah, so we're talking about the times. One of the things that we realized in the first paper is that we only actually took these times into account when we're actually comparing them with the size of the database. But something that we do it in some follow-up work is that we realize that sometimes these parameters or these specific times don't actually hold specifically that well, not if you increase the number of elements in the database, but if you increase the size of each element in that database. And what we realize is that then actually the times increase a little bit not so nicely anymore. So if you're interested in researching something, I will invite you that that's an interesting problem to look at, how to create an efficient PIR scheme that doesn't care that much about the number of elements that the database has, but rather how long each one of those elements is in the database. Okay, so that's the first property, which is efficiency. And maybe I have convinced you already that this is an efficient scheme. Now let's look at the second property that you have to have on PIR, which is security. And how do we define security on PIR? It's basically a thing that is called indistinguishability of client queries, which is the assumption that the server will not be able to guess which specific index you're interested in the database, right? They will not be able to distinguish between different queries. Here, the security is always assuming a semi-honest model in which what we assume is that the server follows the protocol steps correctly and attempts to learn based only on the query. You can debate with me later if this is the best security to actually put in the real world, and I have some opinions about this, but this is the one that we have currently for PIR. How we essentially arrive to security, we are basing our assumptions on NWE. So we actually state that B prime is distributed uniformly under the assumption that decisional LWE is difficult to hold. One of the things also that you might have realized when you're looking at the scheme is that we have a specific A parameter that we just derived that kind of remains the same, right? What I told you is that we derive CBs and CCs, and that are going to be having independent S's and independent E, but the parameter A is going to remain the same. And you might ask me, if that does mean that it's still secure, and I will answer you with yes, it holds. And it turns out that it is still secure. And there's a great paper that actually shows that regex encryption remains secure even when the same matrix A is used to encrypt many messages, provided that each ciphertext uses an independent secret vector S and an error vector E. Now, this also maybe you can argue that for the real world, we should take a precaution here, because it turns out that when you use a specific one of the pairs that you have on your local storage as a client, you should not reuse it again, because if you reuse it, then you're going to be breaking the security of the scheme. Again, what we essentially are interested in proving is this a specific notion that I call it indistinguishability of client queries. And the first thing that you actually prove is that you prove one query's distinguishability, which is easy to prove because we're basing ourselves in decisional LWE. But now we're also interested, for example, in proving L query indistinguishability for an L that, for example, is poly of lambda. How did we actually prove that? Is that we base ourselves on the decisional matrix LWE problem, which actually shows that under standard hybrid arguments, it shows that any adversary that can distinguish between two distributions with advantage epsilon can be used also to construct an efficient adversary, breaking the decisional LWE problem with advantage at least epsilon over L. So what we're basically doing in this specific notion is that we're interpreting each one of the parameters as a matrix, and the security will hold because we were basing ourselves under this standard hybrid argument. If you want to read actually the specific argument and how you do that, this was also proven in the introduction of the Frodo-Chem scheme. So I invite you to also read a specific paper for the specific security proof. Okay, and the specific parameters that we use for this specific scheme are the ones that we just previously defined in some of the previous slides. And we're very conservative, as I told you. So we have a security parameter of 128. We also chose some parameters really conservative because we wanted to use 32 bits. And what you also have in this specific slide is that we arrive to 128 bits of security for 2 to the 52 queries. And the security can increase by increasing the dimension, but this will impact a parameter we call kappa. What is kappa? It's just improvement factor relative to the offline client download compared to the database size. So of course you can make this a little bit nicer and maybe increase a little bit the dimension, but then again, that is going to be having some impact into your offline costs. So we didn't want it specifically to do that, but if you want to play a little bit with the parameters, you can maybe play just a little bit. Okay, so one of the questions that I also come up with is how do we come up with this? And one of the reasons why we realized that this was possible to actually happen is because we were looking at regex encryption. And if you see, this is kind of usually the form how regex encryption is usually presented. This is essentially Frodo PIR. As I told you, this is regex encryption. The only difference is that we're putting a lot of the computation ahead of time. Why? Because we realized that this specific step in which you're adding the specific encrypted ciphertext could actually happen during the client query, but all of the rest of the computation can happen in a pre-processing stage because it's not dependent on that. So what we'll actually essentially do in this paper is kind of fragment regex encryption so that you have some of the steps ahead of time. And we also use a ternary uniform distribution that is usually bounded by 4 on the square of m. I'm not so interested here, but if you want some specific details, you can check them in the paper. So why is this simple? And I will argue that it's really easy to use in the real world is because this is a really simple scheme. So if you go to engineering teams and actually do with them like the specific equation, they will, with high probability, they will guess how it works, even without actually knowing that this is based on lattices, because why they will care about this? But if you actually draw with them the equation, they will realize that it actually works. And it's much more easy to put in production these kind of schemes if your engineering teams are actually convinced of how this specific scheme works. So in this case, it is really easy to explain, and hence it is easier to push for production. It is also simpler to implement. I think a ROS implementation has really few lines of code because we also require no polynomial arithmetic or fast Fourier transforms. We also don't require the server to store any hint related to the client. We do have a hint, but it's only related to the database. Why I put here as a highlight is because if you check in the literature some of the schemes based on ring learning with errors, you will realize that the server also has to store an hint which is related to the clients. And in this case, we don't have to actually store that. And of course, LWE-based PRR schemes are faster and cheaper because the encryption scheme is linearly and not fully homomorphic. So we can use actually more smaller and more efficient parameters. But it is still limiting. And one of the things that you can argue with me is that we still depend quite heavily on the database size. And also, if we actually change a little bit the scheme, we can maybe not be so dependent on the database size, but we were still going to be dependent on the size of each element in the database. Because as I show you, that actually impacts our actual benchmarking. Because as you saw, our times actually increase when the size of the elements that exist in the database are increased. So again, this is an open research question for you if you want, or how to actually make a PIR, which is also not so heavily dependent on the size of each one of the elements that exist in this database. And also many of the steps are dependent on the specific matrix A. We can make it independent as we did in Frodo PIR because the client doesn't have to locally download this specific matrix A, but rather they can just expand it from the seed, but it is still dependent on some of the steps. So if you again want a research question, maybe think about how to make it more independent from this specific parameter A. And something that I will also argue. Okay. And something that I would also argue, okay, it works, okay. Something that I will also argue is that, yes, it seems like this is an efficient scheme. Maybe we can put it in some actual production environments, but this is really, really, really for the real world. We started when we were defining PIR, we were thinking about some schemes in which the database is assumed as an array of M elements. But if you ever work with real database systems, you will know that databases are usually not structured in this way, right? They are oftentimes structured by keywords. There sometimes are structures as JSON elements or graphs or Excel spreadsheets. And it turns out that the PIR schemes that currently we have in the literature are not able to actually work with these kind of structures because they do assume that the database is this representation of an array. So again, if you're interested in researching about this, maybe there's a way to actually think of these other more complex structures and how to use PIR with them. An assumption that we also made at the beginning when I introduced PIR is that we are assuming that the queries are very simple, right? That a client is interested in a specific index that they are querying from the database. But again, if you work with real database systems, you can argue with me that that's not the majority of times what you're interested in. Sometimes you're interested in the union of database systems or in the disjoint of database systems. We currently cannot handle that easily in PIR. And sometimes you're not even interested in a specific value that exists in the database, but only on the nearest elements that are nearer, for whatever definition of nearer, to that specific value it exists in the database. So think about recommendation systems or search engines in which you are not interested specifically on one value, but rather on the recommended, which are the nearer to your query values that exist in that specific database. At the moment, PIR cannot handle that much efficiently. Also, databases are constantly updated. If we go back a lot of slides, you will realize when I actually introduced the scheme that here on the offline phase, we're saving a lot of computational time, right? But we're always dependent on this database. So what happens if the database gets updated? If, for example, elements get added or deleted or there are modifications in place. What happens is that now you have to execute again this offline phase, or somehow you could also maybe just for some specific rows, you will have to re-download the parameters, but that again, that is costly for the client to re-download. So again, if you want to have a database that is constantly updated, this scheme doesn't seem to work anymore. And as far as I know, in the real world, the majority of databases actually get updates. So this is not really that fitting to the real world. It's only fitting for databases that are kind of assumed that are static. And also something that you can argue with me is the security we assume enough. So when I introduced the security that we're trying to achieve in PIR, I basically told you that we are in the semi-honest model where we think that the server is going to be following the protocol steps correctly. But maybe that's not the truth, because maybe it happens that the server is malicious and is really interested in being malicious against you, and they actually change the database or change the specific rows of the database so they can launch a selective failure attack. So it's the security that we assume in the semi-honest model enough, or should we also think about malicious security? And also, should we think about private databases? When I actually introduced the scheme at the beginning, I told you that we are assuming that the database is public and that you know specifically the value that you're querying for, right? The index of the value that you're querying for. But what about private databases that contain like really sensitive information that is legal information or legally bounded, or contains private information that is protected under some privacy law? What happened with those kind of private databases is that we cannot handle currently with some of the PR schemes. Okay, so here I'm going to maybe present you one solution. This is not my work. This is the work of Leo Castro Kiwuli. But the reason why I'm going to present to you is because later we have thought of how to actually expand it. And this is basically on the setting on how to use or how to achieve the malicious security so the server doesn't launch any kind of attacks against your specific queries that you send into the database. And again, I invite you to read this paper. I think it was accepted at Usenix, and it's a really, really great paper. Okay, so I told you sometimes we have these really important security properties. What we want to achieve is malicious security, which in the literature you can also find defined as authenticated or verifiable or malicious PIR. They all kind of mean the same, which is trying to achieve malicious security. If you already remember the scheme that we just presented, the Frodo PIR scheme, or also called simple PIR, you will realize that we already are giving kind of this hint of the database, right? This multiplication of this matrix A times the specific encoding of the database that we call D, and we call kind of this hint as M. So that is the hint. And if you think really hard about it, maybe you can represent that or think about it already as a commitment. So what they do is that once you have this specific commitment, you can accompany that specific commitment by a non-interactive proof of knowledge of the database. And then every answer from the server is verified against this specific proof to ensure that it's consistent with that specific commitment that you just made of the database. So specifically how they did it in paper is that they, again, put themselves into the lattice setting, and they use lattice-based commitments to actually arrive to this malicious security. And what they use is what I think that is called extractable CIS commitments, based commitments. And if you're interested in learning about this specific kind of lattice-based commitments, I invite you again to read that specific paper that I just put on the slide. So how do they look like? Again, if you think of Frodo PIR, we already know that we have kind of this commitment to the database, which we call the M, which is the multiplication of A times D. Then you can actually create a proof of knowledge by sampling a specific challenge that we call C. Then you send that as a client to the server. The server does the multiplication of the challenge times the encoded representation of the database, which we're going to be calling set. Set is sent back to the client. And if you actually check set times A, should be equal to C times M. So with high probability, you will know that that actually is a proof of knowledge that whatever answer was given is really equal to the specific commitment of the specific database that the server has. And that's kind of happening in the pre-processing stage. Now, when the server actually comes back to you with an answer, you can rely on kind of the same idea to construct also a non-interactive proof. In this case, it's interactive, but eventually you can just apply via Shamir and get it non-interactive. But in this case, it's interactive. But essentially, you can create a proof that essentially says that whatever answer is given back from the server is also consistent with a specific commitment of the database that you computed in the offline stage. So how does it look like? Again, this is Frodo PIR. You as a client basically knows the specific value that you're querying for, and you call that the index I. You create a query, which is going to be called B prime. You send this B prime to the server. The server replies with an answer that with high probability will have your correct value, which we call C prime. Once you get C prime, you also sample a challenge, which we're going to be calling uppercase C. We send the challenge. We do again the same multiplication as the server of C times D, which is equal to Z. And then when you actually you send that back to the client, and the client locally does the multiplication, but this time we also multiply it specifically with that value of the query and also the value of the answer, which is B prime and C prime. So this with high probability will pass if indeed the server used the correct commitment to the specific database, which was actually computed during the offline phase. And what you see here is then that we arrived to some kind of malicious security, because now you are actually aware, or you're actually convinced that with high probability, the server is giving you back the correct answer in relationship to whatever commitment of the database they present to you during the offline phase. But is this enough? So one of the things that I already told you when we were talking about these specific commitments is that whatever proof you are actually sending is related to whatever commitment the server gave you of the database. But what happened if the server lied to you and gave you also the wrong commitment to this specific database? Then in this case, the server can still be malicious. So this gives a solid base, but then again, it assumes that there's a public and an honest digest of the database that the server is giving you. So in this case, the server can still cheat. It will not be able to cheat in the answer that it gives you back in relationship with the commitment, but maybe it can cheat with the commitment itself. So the feature work that we're currently doing is actually expanding this so that we have the ability of actually the server actually not being able to cheat in this specific model. And the other thing that we're interested in is how to expand it to PAR. So one of the things that I introduced in this slide is this idea of this commitment. And it's basically, this is an adoption of one specific zero knowledge proof that is presented in this paper that I have listed in this slide. But if you already think about this, this is actually not a zero knowledge proof, right? Because we're assuming a value that is public. We're assuming a value T that is indeed public, and hence we don't need any kind of zero knowledge over here because the value is already public. So what they did in this specific paper is that they toss aside like the zero knowledge property, and they're only interested in the proof of knowledge to something that is binding. So if you actually want to put this in the symmetric model in which you have a database that is actually assumed to be private, what you can actually do is use the zero knowledge proof over that private database. And then maybe you have actually a symmetric PIR scheme. But what happens then is specifically some future work that we have in which essentially now, yes, we can use maybe some new lattice-based zero knowledge schemes and arrive maybe to symmetric security, but you can argue with me, but then what happens and how you make the database private in the specific product PIR scheme? And for that, I invite you to a few weeks where we actually are going to be putting, hopefully, this paper on ePrint on how to expand all of these commitments and zero knowledge proofs based on lattices in the PIR setting, so we also have some symmetric PIR. So just look for it. And the idea here is also that we are always basing all of these primitives on lattice so that we arrive to some post-quantum security, because there's a version in which you can also have symmetric PIR by using, for example, OPRFs. But we're not so interested in this because the current state of OPRFs is that they are not that post-quantum, or if they are post-quantum, they are not so efficient. So what else? And just to be concluded. So if you want to research on this, because now you got very excited and now you really want to work on this. So what are some open questions currently in the literature that you can actually think about it? Some of the things is to expand the security model. As I already showed you, one way to actually expand the security model to have malicious security, that's a really good base. But maybe we need actually more people having eyes at this and actually thinking about maybe how to attack different PIR schemes, because there's also almost no attacks to PIR schemes. So maybe think about avenues to attack. Also think about how some kind of leakage can impact these schemes. What I'm talking about leakage is, for example, think on PIR on the symmetric model in which you have a private database, and you're actually as a client querying against this database, and it turns out that a value doesn't exist in this database, and you replied with this value doesn't exist. Then you actually are leaking something of the database because you're revealing that certain values exist or not. So what impact does this leakage has actually on symmetric PIR? It would be great to also introduce updatable techniques, so you actually can come with an efficient scheme that actually works with updatable databases instead of having to re-download the parameters or having to redo the parameters. That will be great, so think about that. It will be great to also look for other applications of the database systems that we can think of in the PIR way. Why is this important? Because currently in the PIR literature, we're basically applying them to a database that is this representation of M elements that look like as an array. But think about maybe something else, something beyond compromised credential checking systems or certificate transparency logs. Think about of any kind of database system in which you want to also have privacy. And of course, what I already told you, think about how to actually have an efficient PIR scheme in which each one of the elements has a variable length. So they are not a fixed length, because what we assume in the PIR scheme that I just present you is that each element in the database have exactly the same length. So think about maybe actually how to incorporate PIR with variable length elements. If you're interested in ring LWE, maybe think about how to make PIR from ring LWE that already exists in the literature, but also to make it less complex so that it will be easy to translate to the real world. And also, I invite you to look at the state of the art of data structure or graphs or matrix theory, because currently there's a lot of advancement there that maybe we can actually take inspiration for to build like much more efficient PIR schemes. And with that, if you want to check some cool papers, this doesn't mean that I hate all of the other PIR papers. It just means that these are the papers that I think give you a solid base of how PIR works. If you're interested in actually building research upon this, I will invite you to read these papers, which I kind of have categorized onto the specific points that I make in the previous slide. So if you're interested in building PIR out of something, I will invite you to actually read some of these papers. And without an announcement, actually, for the first time in cryptography, there will be a workshop on PIR at PETS, which is happening in a month at the University of Bristol. So if you're interested in talking more about this, I invite you to go to PET and maybe talk about PIR. And also, if you want to join some cool communities, I put also the links over there. And with that, I'm also on time, so thank you very much.
Thank you for the talk, Sophia. Are there any questions?
Thank you for the very good talk. Yeah, it's very informative. I have a simple question. In your slide 14, you mentioned security, you want to 128 bits. That's understandable, seems quite reasonable. Then you also mentioned 2 to the 52 clients. So where this figure coming from?
Yes. So we kind of make that assumption that maybe 2 to the 52 queries, but it's also after we did the actual analysis that all of the lattice parameters will hold. We realized with that security level and the specific dimension of the lattice, then it will mean that the security will hold up to 2 to the 52 queries until we have to resample again this specific parameter A. So yeah, we also have a script of how to actually generate this. So if you want, I can send you like that specific script of how to generate these numbers.
Hi, thank you, Celi. Yeah, thanks for a nice talk. I may miss some information, so I would like to know some general questions about this talk. First thing is that compared with the traditional PQC algorithm-based PIF, so what is the performance for those similar technology-based one? This is, of course, for post-quantum security. But the performance, what is the general comparison?
With other PIR schemes? Yes, so other PIR schemes, it depends on which kind of family. So there are the ones that are based on FHE, for example, which will be more computationally heavy, sometimes for more than like 1 second. And we wanted to have something that was more efficient than that. So what we wanted to Jesus, okay. So what we actually wanted to achieve is something that is of the milliseconds. Of course, compare these to actual systems that doesn't have any PIR, for example, database systems. This is still costly, right? Because when you actually send a query to a database without any kind of encryption, you will have that almost immediately. Like, yeah, you only have to fetch the value from specifically the table and give back. So yeah, but I can send you also like a much more heavy comparison if you want with current PIR schemes that exist in the literature.
Second one is that any standardization progress for PIR now?
Standardization
progress.
Well.
Yeah, organization considerations.
Okay. So what applications? I think it's the question.
Not just application, I mean standardization.
Standardization.
That's right.
Yes, okay, that is a great question. So we're currently not really heavily on pushing on standardizations, though I do participate quite heavily on the IETF. And currently there has been some talks of actually standardizing PIR on the IETF. Why specifically? Because they are interested to use PIR for search engines. So when you actually send a query in your search engines of preference, let's say it's Google, you also make that specific query private to the database that is held by Google, for example. Here is not the usual problem of PIR because, as I told you, this is an instance of what is called KANN PIR problem, in which what you're interested in is sending a long vector with your preferences. Let's say your preferences are sports, Lionel Messi, football, Argentina, and the World Cup, and you're interested that the search engine gives you the best recommendation. This is usually represented as a graph, a proximity graph, in which what you're interested is in the cluster in that proximity graph that is closer to the specific vector, which is a query. So it's kind of like PIR because you're fetching this with this representation of a graph that eventually can be represented as a matrix, but it's not precisely the problem. But that's why in standardization processes, they are interested in this, mostly not in the more lame application of PIR, which is the one that I showed, but more for like recommendation like or search engine like systems.
Sorry, so last one, a short one. So basically, why your scheme is just focused on Fredo similar technology? I mean, whether it's possible extended to consider some similar technology from Kyber or something. Is it possible?
Okay.
Special property of Fredo.
Yes, we wanted to base on the very simple standard LWE because it turned out that it becomes a much more simple and practical to use a scheme and that we arrive to really great efficiency. There's other PIR schemes that are based on ring learning with errors, which is what some of the current post-quantum based schemes on the post-quantum competition are also based at. There's some classical way to also do PIR, but we didn't want to go that way. Or you can also use FHE, fully homomorphic encryption, to also achieve PIR. Okay.
Any other questions? Maybe I have one. So usually, as you kind of mentioned somewhere, so for these like search engines, I guess it's like a keyword-based database, and for this one, it's indices-based. And is there any way to kind of, I don't know,
Yes, so I
that?
have secret slides. Wait a moment. Sorry, I have a lot of slides.
I was just wondering those situations where the clients know the indices, like what is the application for that?
Yes. So that's two kind of questions. So the first one, if it's actually PIR, can also be applied. So keyword-based kind of databases, which are the ones that exist the most. And for that, there's an easy way to kind of do that, in which what you do is that represent this specific map, which is now your database, in which you have some amount of keys and n amount of values, and you represent them like kind of in a filter like a structure. Think of like Bloom filters or maybe cuckoo filters. In a paper that we just published, we use binary fuse filters, but think about of any kind of filter. You represent it as a filter, and then when you actually query, you send this long vector of zeros, except for the specific values that you're interested in the specific filter. So you can actually arrive to keyword PIR that way, which is much more easier to use in the practical world because then you can usually use it with keyword-based databases. The only problem here, again, is that we're assuming that there's a fixed length of each one of the elements in the database, which is not great because JSON-like databases, for example, don't have that. The second question was how to actually guess the index. So there's ways that you can do this. You can always like use a hash. So for example, think of like a database and you want to know the specific password that you're interested in this database. You can index with a hash of that password. And then what you do is you locally query with a specific kind of hash, which corresponds to the index. So you can do like kind of this hash table. Or if you want to make it even more symmetric, you can use instead an OPRF for this. So you like kind of hide specifically what value is referred to. But yeah, there's some techniques.
Okay, great, thank you. Then if there's no more questions, let's thank Sofía again and take a coffee break.